What did the James Webb Telescope actually discover in 2025? Dear traveler, good day. Today, we journey to the edge of the universe, guided not by a spaceship, but by an eye suspended in the void. An eye that pierces the darkness, captures the light of stars that died billions of years ago, and reveals what humanity had never before seen. Because in 2025, the James Webb Telescope crossed a new frontier. Galaxies too ancient to exist, distant planets with strangely familiar atmospheres, and signals that some did not expect so soon. Are we alone in this universe? And what if, somewhere in those dizzying depths, the proof was already hidden, that we are not the first to observe the stars? But before embarking on a new adventure, don't forget to like the video and subscribe to the channel to not miss a thing. Thank you, and have a good journey. The James Webb Space Telescope is often described as the flagship observatory of the 21st century, and not without reason. Since its commissioning, it has embodied a major advancement in our understanding of the universe, thanks to its revolutionary design and state-of-the-art instruments. But what makes it the ultimate device for unraveling cosmic mysteries? To start, James Webb is equipped with a primary mirror, composed of 18 hexagonal segments, carefully assembled to form a surface of 6.6 meters, or roughly 22 feet, in diameter. This segmented architecture allows the telescope to be deployed in space, ensuring a large mirror size while reducing its dimension at launch. These segments, made of beryllium coated with gold, give the telescope exceptional sensitivity. Gold is chosen for its reflective properties in the infrared, as James Webb must capture light emitted by very distant and cold objects. Infrared wavelengths pass more easily through cosmic dust and reveal phenomena invisible to other instruments. Four instruments form the heart of the telescope. Hierarchical, a near-infrared camera, maps the universe in wavelengths longer than the visible. Spec, a near-infrared spectrograph, breaks down light to analyze the chemical composition and physical properties of celestial bodies. MIRI, dedicated to mid-infrared, allows observation of very cold objects like young stars in formation. FGS stabilizes the telescope by guiding its pointing and supports various observation modes. James Webb not only deploys this constellation of instruments, it is located about 1.5 million kilometers, or approximately 932,000 miles from Earth, in a region of space called the second Lagrange point. This area offers a gravitational balance that keeps the telescope in orbit around the Sun, with the Earth and the Moon behind it. This reduces thermal variations and light interference, improving measurement precision. This orbit maintains cryogenic conditions essential for infrared sensitivity. The telescope must remain very cold to prevent any heat emission from its own components. Cooling systems keep the instruments at a few tens of degrees Celsius or tens of degrees Fahrenheit. The slightest heat source could skew the readings. James Webb is also equipped with coronagraphs that block light from bright stars and sometimes reveal the presence of nearby planets. Hubble had already revolutionized astronomy with visible and ultraviolet light. James Webb goes further into the infrared. This evolution is crucial for detecting objects hidden behind layers of gas or observing the first galaxies formed shortly after the Big Bang. Astronomers can thus look further back in time and better understand how structures formed over billions of years. James Webb's infrared sensitivity represents a considerable gain. It offers superior resolution in some wavelengths and observes finer details. Thanks to its large mirror and the precision of its coronagraphs, it opens new perspectives in the study of exoplanets. It is expected to accelerate the search for potentially habitable worlds around distant stars. One of the goals for 2025 is to establish statistics on exoplanets. James Webb will measure the atmospheric composition of dozens or even hundreds of extrasolar planets. By scrutinizing the infrared signals emitted or reflected, researchers will be able to detect molecules like water vapor, carbon dioxide, or methane. Their presence, along with temperature, could indicate conditions conducive to life and reveal the diversity of planetary systems. But its ambition doesn't stop there. Astronomers also plan to probe the depths of the universe at redshifts greater than 14. This means observing galaxies formed a few 100 million years after the Big Bang, at a time when stars did not yet exist. These extreme surveys will allow us to date the formation of the first galactic structures and understand the large-scale organization of matter. James Webb is a pivotal element for current astronomical research. Its segmented mirror, infrared instruments, and positioning make it the most ambitious space observatory ever designed. Its great sensitivity, combined with advanced cooling, ensures it a unique stability to capture light from the cosmic edges. By the horizon of 2025, it promises new discoveries, whether in the nature of exoplanets, distant galaxies, or our understanding of the universe. On January 14th, a major announcement illuminated the scientific community. James Webb has allowed the identification of a population of tiny galaxies, now nicknamed the Little Red Dots. These microgalaxies, with a strong red hue, are extremely dusty and difficult to observe with older instruments. Thanks to its infrared sensitivity, James Webb has spotted several thousand of them, located at redshifts between 2 and 4, at a time when the universe was still young. To understand their importance, we must return to the phenomenon of redshift. The farther a galaxy is, the longer it takes for its light to reach us. Along the way, its wavelength stretches as the universe expands. Observing these galaxies is thus like looking both far into space and back in time. Their light, stretched to the infrared, becomes detectable by James Webb, revealing the most distant cosmic ages. The little red dots are valuable witnesses from the era of the young universe, about 2 to 3 billion years after the Big Bang. They likely harbored processes of low-mass stellar formation, giving birth to small red stars that are very numerous and long-lasting. Understanding their genesis helps illuminate the fundamental mechanisms of star evolution. Their dusty appearance indicates a high concentration of interstellar grains. These grains, composed of heavy elements, stem from ancient stars or supernova explosions. They mix with gas, form larger structures, and nourish the formation of new stars. Their abundance in a young universe suggests that the conditions necessary for chemical synthesis were already in place. Interstellar dust absorbs much of the visible light. These active but discrete microgalaxies thus escaped optical telescopes. Only the infrared allows them to be revealed. Where old missions stopped, James Webb excels. It captures infrared light and uncovers these structures buried under cosmic dust. The observation campaign has allowed the analysis of a vast catalog of dark galaxies, measuring their residual light and estimating their star formation rate. The study of their spatial distribution shows how they interacted with more massive galaxies, participating in a progressive assembly of matter on a large scale. Previously, astronomers had already noticed red objects in deep surveys, but the limitations of older instruments prevented them from being clearly distinguished. Thanks to James Webb, this ambiguity disappears. Its infrared sensitivity allows for systematic detection. We move from a few dozen to thousands of cases, providing a representative sample for studying star formation in extreme conditions. The implications are numerous. This discovery proves that low-mass star formation was already intense in some very young galaxies. It also suggests a greater diversity in galactic evolutionary paths. By studying their infrared brightness, we can better estimate the amount of available gas and dust and deduce the capacity of these galaxies to create new stars. The little red dots could play an essential role in galactic growth. Some models suggest that they aggregate to form larger systems, or that they fuel the growth of other galaxies. Their contribution, long overlooked, could be crucial during the rapid development phases of the young universe. The discovery of these galaxies also prompts a re-evaluation of the distribution of matter in the early universe. By precisely locating these objects, cosmological models can be adjusted. Their environment, interactions, and gravitational impact. All this illuminates the large-scale organization of matter. Finally, the little red dots allow us to test numerical simulation models. By comparing star formation rates, gas quantities, and dust composition with predictions, researchers can refine their hypotheses. Every discrepancy is an opportunity to adjust parameters and better understand the processes at work. On January 20th, the James Webb Space Telescope revealed a fascinating discovery. Two distant galaxies, Cosmos 2063-5829 and Cosmos 2063-5830, show intense star formation while remaining invisible in the optical spectrum. Astronomers call them dark galaxies, as they emit very little visible light. Yet, James Webb's infrared instruments have revealed a sustained rate of stellar creation. According to analyses, this activity is due to the presence of thick dust that absorbs and obscures the light. These galaxies are at a redshift close to 0.8, which means their light has traveled for several billion years before reaching us. The higher this factor, the further back in time we are looking. Detecting such intense stellar activity in almost invisible galaxies demonstrates the power of infrared. Without this ability to capture the thermal radiation of heated dust, this slice of the universe would have remained out of reach. The most surprising aspect concerns a phenomenon called ram pressure stripping. When a galaxy travels through a dense intergalactic medium at high speed, it experiences pressure that pushes some of its gas backward. On a cosmic scale, this mechanism can deprive a galaxy of a large portion of its matter, compromising its ability to create new stars. Examining the two galaxies, astronomers detected gas tails, an irregular distribution of dust, and off-centered star-forming regions. These signs indicate that these galaxies are undergoing, or have just undergone, a gas loss episode. At this level of redshift, this is the first direct evidence of such a process. James Webb's data confirms that even with some gas ejected, these galaxies continue to produce stars in certain zones. Infrared analysis plays a crucial role here. The dust absorbs light emitted by the stars and re-emits it in the infrared. James Webb's instruments precisely detect this thermal signature, which allows the star formation rate to be assessed. Even if these galaxies appear barely perceptible in optics, they reveal sustained activity. Their chemical composition also suggests that several generations of stars have already succeeded there. According to current models, this process can strongly influence a galaxy's evolution by reducing its gas reserves. But as long as some material remains, a resurgence of activity may appear in the still-fed zones. This is what the data shows. Despite the partial gas loss, these dark galaxies continue to form stars at a high rate. Later, their activity could cease for lack of fuel. The environment plays a key role. For such a mechanism to be triggered, the galaxy must pass through a region rich in hot gas. Galactic clusters or matter filaments are ideal environments. By studying the position of the two galaxies in this environment, researchers aim to understand under what conditions the pressure becomes sufficient to alter the structure and fate of the galaxies. On the technical side, it's the infrared sensitivity of James Webb that makes this analysis possible. Its large mirror of 6.6 meters or 22 feet and its specialized instruments allow it to capture the heat emitted by stars at the core of gas clouds. Coronagraphy strategies block direct light, revealing weak signals. Thanks to this precision, scientists have identified for the first time a case of gas loss, compatible with this phenomenon at this stage of cosmic time. The next steps will aim to compare the composition of the expelled gas with that which remains at the center of the galaxies. The researchers also plan to cross-reference these data with those from other ground observatories to better understand the real impact on molecular gas. Measuring the ejection speed will help anticipate their evolutionary trajectory. Will these galaxies maintain their activity or sink into stellar silence? We are on January 29th, at the heart of the cosmic vastness, when the James Webb mission unveils striking new images of a star system named WR-140. Located over 5,000 light-years away, it brings together two massive Wolf-Rayet-type stars. These stars, known for their powerful winds and rapid matter loss, eject immense quantities of gas, creating astonishing structures around them. Thanks to the MIRI instrument on board James Webb, one of these formations becomes visible, a series of concentric dust shells, similar to waves frozen in the void. In a binary Wolf-Rayet system, two stars are closely linked by gravity and orbit each other. When they approach, their stellar winds collide. Particles then condense, forming dust. This dust organizes itself into circular patterns around the pair, like rings forming on the surface of water. Astronomers suspected the existence of these structures, but only the sensitivity of MIRI allows their details to be revealed with unparalleled clarity today. MIRI is the mid-infrared imaging instrument on the James Webb Telescope. It captures wavelengths longer than those perceived by the human eye. It is precisely in this range that cold dust radiates. Invisible in the visible, this material becomes perfectly discernible thanks to MIRI, revealing it against an otherwise black and uniform celestial background. Cosmic dust is composed of tiny grains made of carbon, silicon, and other complex elements. In a system like WR-140, the fast wind of the hot star collides with that of its companion. This shock compresses the expelled matter, an ideal condition for the birth of molecules and solid particles. The images show how these shells extend like bubbles, formed at regular intervals, gradually pushed outward. This phenomenon is essential as it sheds light on how interstellar dust forms. A large part of the dust in our galaxy could come from these stars at the end of their lives. Burning their fuel at a rapid pace, Wolf-Rayet stars have a brief existence, but their end marks intense chemical activity. They enrich their environment with heavy elements and dust, which will later serve in the formation of complex molecules indispensable for life. The shells observed around WR140 show that matter is ejected in successive waves. At each close pass in their orbit, the two stars generate a new pulse of dust. This wave then expands, forming a ring. Over time, the orbit produces a regular succession of waves that overlap in space. The analysis of the geometry of these layers, captured on January 29th, has allowed the measurement of their expansion speed and the tracking of the precise rhythm of the formation cycle. This rhythm is not instantaneous. It sometimes takes several years for the two stars to reach their maximum proximity again. Each time they come closer together, a new shell appears. By studying the different layers, astronomers can estimate how often these waves are produced and with what intensity. This data allows testing theoretical models, describing the dynamics of stellar winds in binary systems. But researchers are also interested in the composition of the dust. MIRI's sensitivity could soon allow a more precise distinction of the present elements. A strong carbon signature, for example, would indicate a carbon-rich Wolf-Rayet star. This distinction has important implications on internal nuclear reactions and on the types of molecules dispersed in the galaxy. Identifying these categories of stars is crucial to understanding how they enrich their environment. Beyond pure science, these images have a strong educational potential. It's rare to be able to observe such organized structures in an environment as chaotic as interstellar space. The shells of WR140, with their regular curves, offer a glimpse of the hidden harmony behind the violent phenomena of stellar end-of-life. These images help raise public awareness of the evolution of massive stars, their chemical importance, and the progress made possible by instruments like James Webb. February 18th marks a remarkable breakthrough. The James Webb Space Telescope has detected infrared bursts coming from the supermassive black hole located at the center of the Milky Way, in the region known as Sagittarius A star. This galactic nucleus, long hidden by a thick veil of gas and dust, remained difficult to observe. Thanks to its infrared light sensitivity, James Webb was able to penetrate these opaque clouds and reveal a series of unexpected and brief luminous flares lasting 20 minutes. A feat that offers an unprecedented view of the accretion mechanisms around this invisible core. A supermassive black hole is distinguished by its gigantic mass, often millions or even billions of times greater than that of the Sun. In our galaxy, Sagittarius A star reaches about 4 million solar masses. This type of object produces no light. Its gravitational field is so intense that no matter or radiation can escape beyond the critical boundary called the event horizon. But just before this limit, matter swirls at a dizzying speed, heats up to millions of degrees Fahrenheit, and releases considerable energy. This radiation, notably in infrared, is precisely what James Webb captured. The recorded burst that day lasted 20 minutes, a sudden peak of infrared light, then a rapid decline, a typical behavior of a very localized phenomenon. In astrophysics, the shorter the event, the smaller its source. These bursts were thus born very close to the black hole, where the gas reaches extreme density and speed. They could result from magnetic instabilities or abrupt variations in the matter feeding. This is where James Webb showcases its full power. Located about 1.5 million kilometers or 932,000 miles from Earth in a stable zone, it enjoys a perfectly clear environment. Its cooled detectors record the slightest thermal fluctuations. Interstellar dust, opaque invisible light, becomes transparent in infrared. The telescope can thus continuously monitor activities in the galactic center, minute by minute. These bursts are linked to the dynamics of the accretion disk. In this rotating zone, the gas rubs, heats up, and radiates. Sometimes, the magnetic field lines suddenly restructure, releasing an excess of energy in the form of an infrared flash. Other models suggest the sudden arrival of a dense cloud or disturbance in the disk. Each burst then becomes a valuable clue to understanding how matter collapses onto the black hole. But the interest doesn't stop there. These observations allow testing the foundations of general relativity. Very close to the event horizon, gravity distorts space-time. Comparing the intensity and frequency of bursts with theoretical predictions allows verifying if Einstein's equations still hold. So far, the data match, once again confirming the robustness of the relativistic framework. This work also shows how essential multi-wavelength approaches are. Radio waves give us the global shape of the system. X-rays reveal the most energetic phenomena. Infrared, on the other hand, provides a detailed reading of heat and hidden structures. Together, these data paint a coherent and nuanced portrait of the galactic center. If these bursts are frequent, they might follow a regular rhythm. If they are rare, they indicate isolated events. Researchers plan to multiply observations to create a reliable statistical picture. Each detection will help better understand the accretion rate, the organization of the magnetic field, and the structure of the spiral gas. Data from February 18th show that a single impulse can appear and vanish in an instant, revealing the violence of the process. Success does not only come from the instrument's sensitivity. The 6.6 meters or 22 feet mirror captures an exceptional amount of light. The sun shield protects the entire system from thermal interference. This technological configuration makes James Webb the ideal tool to explore the dense and hot regions hidden at the heart of the Milky Way. The bursts detected that day confirm the relevance of this mission. Today is February 26th. The James Webb Space Telescope unveils a fascinating discovery. Some protoplanetary disks around small stars known as M-dwarfs persist much longer than expected. These celestial bodies, much lighter than our Sun, retain rings of gas and dust around them for over 12 million years. Until now, it was thought that these structures dispersed much earlier. This revelation upends our understanding of the conditions necessary for the birth of new planets. A protoplanetary disk is a remnant of star formation. It is a reservoir of gas and dust in orbit, destined to give birth to planets. Normally, stellar winds disperse these materials after a few million years. But with M-dwarfs, this process seems slower, thus opening a wider time window for the formation of new worlds. These stars emit less heat and light. Their cores evolve more slowly, and their winds are gentler. As a result, the gas remains trapped around them longer. This additional time leaves more material available to form planets, even in the outermost regions of the disk. Until recently, astronomers thought these disks disappeared after 5 or 6 million years. However, the spectral data collected by James Webb show that they can last well beyond that. The infrared signature indicates the presence of silicates, dust, and sometimes even ice. Around some M dwarfs, the dust level remains surprisingly high, proving that not all systems follow the same evolutionary path. This discovery reignites the question of gas giants. Can we imagine planets like Jupiter or Saturn forming around these small stars? Usually, it is assumed that they must form very quickly before the gas disperses. But if this gas lasts longer, then even modest stars could host massive worlds, provided there is enough material. From a habitability standpoint, the finding is just as promising. A disk prolongs the presence of environments rich in dust, suitable for complex chemical reactions. These molecules, slowly organizing themselves, could form the first building blocks of life. The magnetic field present around some M dwarfs also influences the disk dynamics, accelerating or slowing certain material movements. The James Webb instruments, operating in the infrared, are perfectly suited to capture these subtle signs. The observations from February 26th reveal systems where the star's mass is only a tenth of that of the Sun, yet the disk remains intact after more than 12 million years. Scientists are now looking to determine whether this phenomenon is common or exceptional. In any case, this discovery suggests greater flexibility in planetary formation scenarios. However, additional observations will be needed to refine the chemical understanding of these disks. Identifying molecules such as water, carbon dioxide, or other life-essential components will be a decisive step. The study of infrared polarization will also allow us to map dust and identify areas where planets may already be forming. This announcement nurtures a discreet but real hope. If these disks persist, then forming planets benefit from more stable and longer conditions. Some models require rocky worlds to form in chemically active environments. Thanks to this extended duration, these reactions could indeed occur. These hypotheses will need to be confirmed by other observational campaigns, but this February 26th will remain a key date. On that day, James Webb showed that even the smallest stars could host rich and enduring systems. In the future, other M dwarfs may reveal even older disks, challenging predictions. These results pose a fundamental question. Do these stars host worlds more varied than previously thought? It will be necessary to study their planetary population in detail to answer this. Thanks to James Webb's sensitivity, exploring this diversity is now possible. On March 7th, the near-infrared camera of the James Webb Space Telescope, or NIRCam, captured one of the most striking spectacles of star formation in the L483 region. Located several hundred light-years away, this area houses an embryonic binary immersed in a dense cloud of gas and dust. The images reveal bright bipolar cavities, carved by powerful jets, shaping the surrounding environment. This observation unveils the fundamental mechanisms of accretion and ejection in the early stages of a forming stellar system. An embryonic binary corresponds to two gestating stars originating from the same matter reservoir. Their cores are not yet hot enough to initiate fusion, so they are referred to as protostars. Each accumulates gas from an accretion disk, while a fraction of this material is expelled as opposing jets. This phenomenon sculpts the observed cavities. In L483, the shape of these structures is evidence of the combined action of gravity, magnetic fields, and the system's rotation. The jets, called bipolar, appear when gas drawn by the protostar is accelerated and then projected along magnetic poles. This flow carves out voids in the cloud, repelling material at high speed. The NIRCam, sensitive to infrared, captures this light filtering through the dust. It reveals the complex structure of the cavities and confirms the presence of two distinct accretion centers at the heart of L483. The accretion rate is estimated at 10 to the power of -4 solar masses per year. Each year, the system absorbs a tiny amount of matter. Over a few 100,000 years, this accumulation allows the protostars to reach the mass and temperature necessary for fusion ignition. Researchers estimate that competition for gas in a binary system strongly influences the final mass and luminosity of each star. In L483, the jets form symmetrical lobes that carve corridors around the central disk. These corridors sometimes reveal extremely cold zones at 250 degrees Celsius or 418 degrees Fahrenheit due to the absence of a direct heat source. Yet, within the disk, magnetic interactions locally warm the gas. This coexistence of icy regions and warmer ones makes the whole very heterogeneous. Infrared exposure shows these contrasts with unparalleled clarity. The orientation of the jets provides clues about the system's architecture. It helps deduce the inclination of the disk and the rotation speed of gas around the protostars. These data are essential to compare observations with theoretical models, which predict specific configurations based on magnetic fields and initial conditions. Every detail enhances our understanding of binary systems, where multiple stars form in parallel. Infrared is the key to unlocking the secrets of L483. Masked in visible light by thick dust, the region becomes readable thanks to James Webb's sensitivity. Positioned at a stable point in space, it detects the faintest signals. Recent images show a binary in full transformation, fueling numerical simulations aimed at better understanding the influence of accretion on the evolution of multiple systems. Each shot reveals the energy of this star cradle. Infrared data also reveals the composition of the gas. In the cavities, scientists sometimes identify water or simple organic compounds. These molecules, born in extreme conditions, could be the first links in a more complex chemistry. Their presence makes L483 an ideal site to explore processes that later could lead to planet formation. At this stage, the accretion rate can vary drastically, causing bursts of brightness or calmer phases. Researchers monitor these variations to understand how the system regulates the influx of matter. Magnetic instabilities or interaction between the two protostars could disrupt the flow. Gradually, the accumulation of gas will lead to the birth of two distinct stars. The cloud will dissipate, and the binary will emerge in the open. As this binary evolves, astronomers plan other observational campaigns to track the possible appearance of individual disks around each star. These structures could be the seeds of future planets. By scrutinizing L483 and its counterparts, science draws the outlines of a cosmic story still unfolding. A new chapter of star formation writes itself before our eyes. On March 10th, a major advancement illuminates our understanding of primordial galaxies. The James Webb Space Telescope has directed its gaze toward a galaxy located nearly 13.8 billion light-years, approximately 8.6 billion miles away. It is thought to have existed less than 300 million years after the Big Bang, a time when the universe was just beginning to structure itself. At the heart of this observation is a spectrum captured by the NIR-SPEC instrument. This near-infrared spectrograph breaks down the light to reveal chemical signatures. Researchers detected the presence of doubly ionized oxygen, a highly energetic form of oxygen. This discovery suggests that a process of heavy element creation had already started much earlier than expected. Oxygen is produced in the core of stars by nuclear fusion. When they die, these stars release these elements into the interstellar medium, enriching their environment. Spotting this oxygen in such a young galaxy indicates that at least one generation of massive stars had already lived and perished, an accelerated life cycle at the very dawn of the cosmos. Scientists use the term metallicity to refer to the proportion of elements heavier than helium and hydrogen. In this case, the presence of oxygen indicates high metallicity. Yet, classical models state that the initial universe was composed almost exclusively of primordial gas. Discovering such chemical richness so early upsets established chronologies. The primitive universe seems to have been more active, more fecund than expected. The infrared spectrum obtained with NIR-SPEC captures the light from extremely distant objects. The expansion of the universe stretches this light, causing it to shift toward infrared, a phenomenon known as redshift. By measuring this stretching, astronomers estimate the galaxy's age and place it within the first few 100 million years of cosmic history. The detection of this doubly ionized oxygen implies that the formation and destruction of massive stars had already ensued. These stars, brief but powerful, produced heavy elements, which they scattered through explosions or strong winds. This scenario reinforces the idea of a young universe already driven by complex nuclear processes. However, the data must be interpreted rigorously. It is necessary to verify that the observed signal does not result from a secondary phenomenon or instrument noise. NIR-SPEC's calibration requires extreme precision. Each point of light must be carefully isolated to confirm it is indeed oxygen. Despite these constraints, the initial results seem solid and widely validated by the scientific community. This discovery raises questions about the mechanisms of rapid chemical enrichment. How could the universe produce so many elements in such a short time? Some suggest that matter was denser, promoting collisions and rapid star formation. Others mention the first stellar generations, called Population 3, capable of creating heavy elements with unprecedented efficiency. In any case, this galaxy pushes the limits of our models. In parallel, this result revives an old debate. Is nucleosynthesis uniform throughout the universe, or have certain environments evolved faster than others? If other galaxies as young as this one show the same characteristics, we will need to reassess our linear vision of cosmic chemistry. If it remains an exception, this galaxy is nonetheless a fascinating case. The observation was made possible by the extreme sensitivity of James Webb. From its stable location at about 1.5 million kilometers or 932,056 miles, it benefits from constant cooling and protection from heat sources. Its infrared detectors, plunged into the cold of space, capture the faintest and most distant signals. This technological leap opens access to objects previously out of reach. Future campaigns will help refine this discovery. If other galaxies show similar signatures, it will redraw the scenario of stellar formation. If not, this isolated case will demonstrate a unique path in chemical evolution. Whatever follows, March 10th will stand as a major milestone in exploring the origins of the universe. March 24th marks an unforgettable date in the history of astronomy with the striking discovery of a phenomenon dubbed the cosmic tornado. This structure, designated as HH49 and 50, belongs to the family of Herbig-Haro objects. These spectacular phenomena arise when jets of material ejected by young stars collide with the gas and dust of the interstellar medium, generating luminous shock waves visible with very sensitive telescopes. In the specific case of HH49 and 50, the images reveal an astonishingly complex spiral shape. The nickname cosmic tornado evokes this whirlpool formed by the interaction between the jet of a protostar and its environment. Astronomers were able to observe this scene thanks to a composite image obtained by combining different wavelengths provided by a next-generation space telescope. The goal was to understand how a supersonic gas jet manages to traverse a nebula and produce such intense light. This image combines visible and infrared data. The visible domain reveals the most brilliant structures, while the infrared unveils the heat emitted by the gas and dust heated by the collisions. Some areas reach several thousand degrees, while others remain much cooler. This fusion of data allows precise localization of impact points between the jets and dense clouds. Herbig-Haro objects appear around still very young stars, often hidden in cocoons of gas. These stars have rapidly rotating disks of matter, fed by abundant reserves. Under the effect of gravity, their cores contract, heat up, and eventually trigger nuclear fusion. During this process, gas jets burst at high speed in both directions. These jets create the visible shocks in HH49 and 50. The image also shows, in the background, a spiral galaxy. It discreetly appears behind the luminous filaments of the cosmic tornado. Thanks to the high resolution of the telescope, its extended arms and bright core are clearly distinguishable. This superposition of two phenomena, one local and the other distant by millions of light years, offers a fascinating perspective. It allows observing in a single scene the birth of a star and the majesty of a vast galactic ensemble. This visual coincidence has inspired studies on the absorption of light by dust. By observing HH49 and 50, researchers note that the material ejected by the star can obscure certain regions of the galaxy situated behind. They analyze luminosity variations to assess the density of the jet in the impacted area, thus refining their understanding of the phenomenon while gathering data on the background galaxy. It's a true open sky laboratory. The telescope used has a large main mirror and specialized infrared instruments. Thanks to this technology, light travels more easily through dust, revealing stars in formation and the dynamics of their jets. This technological advancement allows us to better understand the early stages of star formation and how matter is distributed in our galaxy. By closely studying the interactions in HH49 and 50, astronomers discovered that the speed of the jet exceeds several hundred kilometers per second or several hundred miles per second. This gas flow, when hitting its environment, produces shocks that ionize the matter, generating a detectable glow. Over time, These shocks create filamentary patterns, signatures of an intense energy exchange between the forming star and its environment. Dust plays an essential role here. It reflects some of the emitted light and allows tracking of the jet movements. By analyzing these data, researchers refine their numerical models on starbirth. Each image reveals a little more about the behavior of cosmic fluids, their composition, and the organization of matter around a stellar core. For astronomy enthusiasts, this cosmic tornado and the background galaxy remind us of the vastness and diversity of the universe. Local phenomena rub shoulders with colossal structures, and modern imaging allows these scales to be brought together in one frame. This visual richness fuels wonder and stimulates new observation campaigns. With each mission, the precision increases, and the surprises continue, bringing more and more knowledge. In the future, new instruments will allow us to delve even deeper into the secrets of this cosmic whirlwind. Each discovery sheds more light on the grand tableau of star formation. On March 27th, astronomers celebrated a major breakthrough with the detection of a full Einstein ring. This phenomenon, predicted by Albert Einstein in the early 20th century, occurs when the light from a distant galaxy is bent almost perfectly by the presence of a colossal mass placed between it and the observer. In this case, the alignment is so precise that the image of the galaxy appears as an almost closed, luminous circle. This gravitational lens offers a tool of exceptional power for probing the distant universe, revealing details otherwise invisible. It also acts as a natural laboratory for studying dark matter. To grasp the significance of this discovery, it is necessary to recall the principle of gravitational lensing. According to general relativity, a mass deforms space-time like a weight placed on a stretched canvas. A massive galaxy can thus bend the path of light grazing it. If the alignment with a background galaxy is almost perfect, this light forms a circle around the foreground mass. The observation of such a complete ring indicates ideal alignment and a gravitational distortion of rare precision. On the same day, the James Webb Space Telescope revealed a striking image of a distant spiral galaxy encircled by this luminous ring. Thanks to the exceptional sensitivity of its instruments, the telescope was able to detect the most subtle variations of infrared light. The sharp outlines of the circle testify to a perfectly symmetrical deformation. Between the observer and the source galaxy, the lensing galaxy exerts a major gravitational influence, essentially linked to the presence of dark matter. This dark matter, invisible, cannot be detected directly. It emits neither light nor heat, yet its gravitational effects are measurable. By analyzing the shape of the ring, researchers deduce the distribution of this mysterious mass in the lensing galaxy. Each variation in curvature illuminates the hidden structure of this matter, allowing for adjustments to cosmological models. The observation thus becomes a full-scale test for the fundamental laws governing our understanding of the universe. The image captured by James Webb was made possible by its stable position about 1.5 million kilometers or 1 million miles from Earth. From this privileged observation point, it detects weak signals emitted by cold or distant objects. In the case of this ring, the instruments reveal fine details, such as slight distortions in shape, potentially indicating the presence of small dark matter concentrations or satellite galaxies. These subtleties feed the study of cosmic structure on a large scale. It is also necessary to measure the immense distance between the source galaxy and the lens galaxy. The photons traveled for billions of years before reaching the telescope's sensors. Their path was deflected by gravity, redistributing the light onto a circle. This exceptional configuration confirms the predictions of general relativity for a perfect alignment. It is a rare moment where theory and observation meet with such precision. Practically, researchers can create a map of the mass present in the lens galaxy. By comparing the light intensity and the geometry of the ring, they reconstruct how the mass is distributed. The ring also acts as a giant magnifying glass, amplifying the light from the source galaxy and revealing internal regions like spiral arms or star-forming areas. Each additional detail enhances our understanding of galactic dynamics through the ages. On April 16th, the James Webb Space Telescope reveals a stunning discovery, the oldest spiral galaxy ever observed. Despite its great cosmic age, it exhibits a structure surprisingly similar to that of our Milky Way. Located through the Panoramic Observation Program, this galaxy is situated at a redshift of about 6.2. This figure means that we perceive it as it was when the universe was just over 1 billion years old. A spiral galaxy consists of a rotating disk of stars, gas, and dust, crossed by curved arms winding around a central nucleus. Our own Milky Way is the emblematic example of this. However, according to traditional theories, such an organization takes a long time to set up. Yet this galaxy already shows a well-structured disk, stable rotation, and defined arms, challenging established models. Redshift measures how much the light from a distant object has been stretched by the expanding universe. The higher it is, the further the object is in the past. A galaxy with a redshift of 6.2 appears as it was barely 1 billion years after the Big Bang. With the current age of the universe estimated at 13.8 billion years, this gives this galaxy an exceptional place in cosmic history. Early simulations predicted that the instability of the young universe would make rapid spiral disk formation difficult. But the data here reveal a well-established dynamic, with regular rotation and a gravitational potential stable enough to support the structure. These observations suggest that some environments allowed a faster organization than previously thought. Astronomers used spectroscopy to analyze the chemical composition, rotation speed, and star formation rate in this galaxy. The results show a varied population of stars, from the oldest to the youngest, indicating a stellar formation history spanning several 100 million years. The interstellar gas follows an orderly distribution, comparable to that of closer galaxies. To obtain this information, James Webb combined several wavelengths, especially in the infrared. This allows it to penetrate dust clouds and detect star-forming regions. The aim is to verify if the disk's rotation follows the same laws observed in the current universe. If so, this proves that stable structures could exist from the start. The study also focuses on dark matter halos, this invisible substance that is thought to exert gravitational influence on galaxies. Until now, it was believed that it would take more time for these halos to form and stabilize a disk. But the existence of this galaxy suggests that dark matter can organize more quickly than expected, consolidating rotation from the earliest phases. Another clue, the distribution of metals. These elements, heavier than hydrogen or helium, are produced in stars. Their presence here implies that several generations of stars had already succeeded each other, enriching the gas of the disk and favoring the formation of spiral arms, a chemical signature that speaks volumes about the early maturity of this galaxy. The panoramic program, combined with data from James Webb, has mapped this spiral with unprecedented precision. The images reveal a bright central bulge, starry arms, and perhaps a supermassive black hole at the center, similar to our own galaxy. This hypothesis remains to be confirmed, but it reinforces the strange resemblance to the Milky Way. This discovery necessitates a re-evaluation of certain hypotheses. If spiral galaxies already existed in such a remote era, then the mechanisms of stabilization, gas cooling, and gravitational structuring may have acted much faster than expected. This opens a new window into the early stages of galactic disks. Finally, this spiral galaxy, confirmed by James Webb's observations, attests to the unsuspected richness of the young universe. An orderly structure, born amidst the cosmic chaos, revealed today thanks to a telescope that redefines the boundaries of our knowledge. April 18th marks a crucial advancement in understanding the universe, thanks to the James Webb Space Telescope. This scientific milestone relies on the creation of a map of galactic distances with unprecedented precision, obtained by the meticulous analysis of light emitted by extremely distant galaxies. Measuring such distances seems inconceivable at first glance, as no physical instrument can reach these depths. However, certain precise clues present in the light of distant stars make this feat possible. Among them are the breaks in the Balmer series, spectroscopic markers related to hydrogen, essential for probing the confines of the cosmos. James Webb, a partial successor to Hubble, is positioned about 1.5 million kilometers, or 932,000 miles from Earth, in a stable zone allowing the elimination of light and thermal interferences from our planet. Its mirror, 6 meters or 20 feet wide, consists of 18 segments adjusted with extreme precision. Thanks to its instruments specializing in the infrared, it captures the faintest radiations emitted by regions as ancient as the first galaxies that appeared after the Big Bang. To measure the distance of a cosmic object, astronomers rely on the redshift. As the universe expands, the wavelengths of light stretch, shifting their hue towards the red. The farther a galaxy is, the more pronounced this shift is. By analyzing the known spectral lines of hydrogen and other elements, and measuring how much they are displaced, it becomes possible to trace back to the time when this light was emitted, and thus estimate the corresponding distance. The Balmer series groups spectral lines produced when an electron in a hydrogen atom changes energy levels. These lines appear at specific wavelengths. Sometimes, astronomers detect a distinct break in the light of a galaxy, where these lines should be. It's the Balmer series break. This marker is used to accurately calculate the redshift and distance. On this 18th of April, James Webb enabled the simultaneous collection of a vast amount of data, thanks to its infrared spectrographs and cameras. Researchers were thus able to chart a curve describing the evolution of the universe's expansion rate according to the redshift, with greater precision than what was achieved by Hubble. Thanks to its increased sensitivity, Webb makes it possible to include much older galaxies, significantly reducing margins of error. In concrete terms, the telescope detects the infrared signals emitted by hydrogen. Researchers then identify the Balmer series breaks, marked discontinuities in the light spectrum. These disruptions indicate how long the light has traveled. By multiplying observations of galaxies located at different stages of their evolution, a vast database is obtained, each galaxy becoming a point on the curve of cosmic expansion. Once connected, these points trace the evolution of this expansion through the ages. This multi-point method proves valuable when astronomers sometimes encounter difficulties in detecting clear spectral lines. When galaxies are very far away, their spectrum can be weak or blurred. The Balmer series break, however, stands out clearly, reducing the risk of error. Its position and intensity provide a reliable measurement of the redshift. To achieve these results, the telescope's detectors must operate at extremely low temperatures, close to minus 230 degrees Celsius, or minus 382 degrees Celsius. This cooling minimizes thermal noise and allows for the detection of the faintest signals. This sensitivity is essential because the light received has traveled through space for billions of years. The implications of this advancement affect both specialists of distant galaxies and cosmologists, modeling the universe's global structure. Understanding cosmic expansion also involves questioning the nature of dark energy, dark matter, and ordinary matter. Each new measurement refines our knowledge of the universe's expansion rate. Some models predict an acceleration, while others suggest more subtle variations. Only a detailed curve can differentiate these hypotheses. This date also marks the integration of the Balmer series cuts as a second pillar for measuring distances, alongside Type Ia supernova used as standard candles. Thanks to this dual approach, it becomes possible to distinguish between perceived and intrinsic luminosity, enhancing the reliability of estimates. The database thus constituted will be shared with researchers worldwide. It will be used to date large cosmic structures, evaluate star formation rates, and trace the major stages of cosmic gas ionization. Everyone will benefit from the infrared precision offered by James Webb. This work relies on meticulous instrument calibration. Each detector and optical element must operate in perfect harmony. Signals are compared to references and then analyzed by specialized software. The slightest error in wavelength processing could skew the results. At this scale, rigor is absolute. It is a remarkable feat, measuring the distance of a galaxy through a simple shift in a hydrogen line. This shift becomes a witness of time, a marker of the universe's evolution, a thread stretched across billions of years. The mapping of galactic distances through the Balmer series cuts is a pillar of the James Webb mission. The results of April 18th allow for a finer curve of cosmic expansion, revealing the potential role of dark energy. Some galaxies observed date back to several 100 million years after the Big Bang, offering a dive into the origins. On April the 29th, an international team of astronomers revealed an exceptional observation made possible by the collaboration between the James Webb and Hubble Space Telescopes. They discovered a group of galaxies dating back 6.5 billion years, providing a stunning view of a primordial stage of the universe. Through this image, we witness the beginnings of a phenomenon known as hierarchical merging, where galaxies approach, interact, and eventually unite to form increasingly large structures. The nickname white gold comes from the shades visible in the composite image. The white areas indicate the presence of older, cooler stars, while the golden hues indicate regions where new stars are being born, releasing energy and illuminating their surroundings. This contrast reveals a simultaneous stellar cycle. Some stars are ending their existence, while others are beginning theirs, still shrouded in gas and dust. Hierarchical merging helps to understand the evolution of astronomical structures. In the early days of the universe, galaxies were smaller and more irregular. Gradually, they began to draw closer under the influence of gravity. With each interaction, their disks and halos deformed, their gases mixed, sometimes colliding. These successive mergers gave birth to more massive galaxies with dense cores and extended halos. The white-gold group precisely illustrates this ongoing process. The image reveals an interwoven network of galaxies with disturbed shapes. Some stretch out in long trails, while others show bright cores with high densities. Thanks to the alliance of James Webb for infrared and Hubble for visible and ultraviolet, astronomers could draw a complete picture of dust, gas, and stars. The infrared reveals hidden structures, while the visible illuminates the active stellar population. Measuring the distances between the components of the group is essential. Researchers use spectroscopy, which allows them to identify chemical elements in light. By detecting the lines of hydrogen, helium, or heavy metals, they estimate the redshift, related to the expansion of the universe. This redshift confirms that the galaxies are indeed part of the same cluster, and not a chance alignment. The analysis of the overall mass of the group indicates at what stage of fusion it is and the probability of an imminent interaction. To better visualize the concept, imagine a constantly transforming puzzle. Each galaxy represents a unique piece, with its own stars, gas, and invisible matter. Under the influence of gravity, these pieces come together, interlock, and reshape the overall structure. The white-gold group shows this particular moment when the pieces begin to assemble. Astronomers study tidal effects, gas redistribution, the birth of truncated spiral arms, and the emergence of star nurseries. The analysis of this observation is ongoing. Researchers examine the distribution of shades, the speed of the galaxies, and compare their results with numerical simulations based on the laws of gravity and plasma. These models trace the history of the group and anticipate its future. They also reveal how invisible matter shapes mergers. By observing the relative speeds, scientists deduce the total mass and estimate the share of invisible matter present in the cluster. James Webb, operating at very low temperatures, captures the faintest signals. Hubble, in Earth's orbit, complements the observations with its surveys in visible and ultraviolet light. Together, these data offer a detailed view of the internal dynamics of the white-gold group. Astronomers can thus follow with unparalleled precision the key stages of hierarchical fusion. It is May 12th, and the Space Observatory directs its instruments towards Jupiter, the largest planet in the solar system. Its immense and swirling atmosphere hosts spectacular luminous phenomena. Thanks to observation in the mid-infrared, auroras 100 times more intense than those on Earth have been revealed. To understand these ribbons of light that dance at the poles of the giant planet, one must delve into the depths of its electromagnetic environment. Jupiter is a planet composed of hydrogen and helium with a dense central core. The pressure becomes such that it generates exotic states of matter like metallic hydrogen. This phenomenon powers a magnetic field of exceptional strength, amplified by a rapid rotation that completes in 10 hours. Auroras form when electrified particles interact with this field and are directed towards the poles, producing intense light. On Earth, polar auroras come in green, pink, or violet. These hues are linked to reactions of atoms in the Earth's atmosphere. On Jupiter, conditions are quite different. Infrared reveals much brighter luminous structures, indicative of significantly more powerful magnetic activity. The particles responsible for these auroras come from the solar wind, but also from moons like Io, which is very volcanic. This ionized material is trapped in Jupiter's magnetic environment and guided to the poles, where it creates complex luminous arcs. The mid-infrared allows one to penetrate the cloud layers and measure the heat emitted by the molecules, revealing the dynamics of the magnetic field. The luminous patterns change rapidly, their intensity varying with the solar wind activity. During peaks, particles pour in, raising the temperature in auroral zones by several hundred degrees, around 100 degrees C to 260 degrees C or 212 degrees E to 500 degrees E. This thermal elevation in the upper layers shows the power released by these magnetic interactions. This May 12th, the captured images made it possible to map the auroras with unprecedented precision. Scientists tracked their formation, movements, and transformations, observing how the planet's rotation and the solar wind altered their behavior. By recording these phenomena over several hours, they reconstruct their evolution, laying the foundation for a better understanding of giant planets. The study of these auroras goes beyond visual spectacle. It sheds light on the relationship between the magnetosphere and the atmosphere. The magnetosphere, an area of magnetic influence, extends tens of millions of kilometers, or tens of millions of miles, around Jupiter. The larger it is, the more particles it can capture and produce luminous phenomena of rare intensity. Infrared spectra also reveal the composition of gases in auroral regions. Ionized hydrogen molecules and excited elements appear clearly. By comparing signatures in these regions with those in calmer zones, researchers trace the distribution of gases and monitor temperature variations. These data are compared with results from probes that have flown over Jupiter, improving the accuracy of theoretical models. Observing these auroras means discovering a ballet of high-energy particles, propelled by Jupiter's rapid rotation and the thrust of the solar wind. Each luminous pulse is born from a collision, and infrared records these moments with precision. We discover giant arcs and invisible currents sculpted by the magnetic field. Astronomers seek to trace the path of the particles, to understand the reactions that amplify their glow when they reach the atmosphere. It is a meticulous analysis made possible by the extreme sensitivity of the instruments. This image from May 12th is not just a visual feat, but a scientific milestone for better understanding the functioning of giant planets and their magnetic activity. On May 21st, the James Webb Space Telescope made a major discovery, the observation of a galaxy named MOEM-Z14. Behind this name lies the object considered the most distant ever detected, with a redshift of 14.44. This phenomenon, linked to the expansion of the universe, translates the stretching of light emitted by a distant source. The larger the redshift, the farther the galaxy is, and the younger the universe was when this light was emitted. MOEM-Z14 is thought to have formed about 280 million years, or about 280 million years, after the Big Bang, at a time when the universe was just beginning to organize itself. Its detection relies on the performance of the James Webb Telescope, capable of observing in the infrared. This sensitivity makes it possible to capture light shifted from very distant objects. Through spectral analyses, astronomers have identified signs of an active, concentrated, and very dynamic galaxy. The data shows an exceptionally high star formation rate in a small area, suggesting an episode of accelerated matter condensation. At such an early stage of the universe, such activity raises questions about the speed of appearance of the first complex structures. To assign MOM Z14 the status of the farthest galaxy, researchers determined its light age. They measured the interval between the emission of its light and its reception on Earth by analyzing the light spectrum. Certain characteristic lines associated with elements like hydrogen or carbon appear shifted. This shift indicates both the distance and the time of emission. For MOM Z14, the result places its light at only 280 million years, or about 280 million years, after the Big Bang, making it an essential milestone in the galaxy chronology. The data also reveals that MOM Z14 already harbors a dense and mature star population. This raises questions about the speed of galactic formation in such an early environment. A starburst core, an area of intense activity, could explain this rapid evolution. A quick gas collapse and sustained accretion could have fueled this growth. Thanks to the sensitivity of James Webb, it is possible to detect clues of ionized gas or heated dust, signs of explosive star formation at the origins of the universe. This advancement relies on the instruments on board the telescope, like its infrared cameras and high-precision spectrographs. The devices were designed to ensure maximum stability and avoid any interference. MOM Z14, emitting primarily in the far infrared, required specialized detectors. Installed far from Earth at an ideal position, the telescope operates in a stable and cold environment, essential conditions for capturing signals as faint as those of this galaxy. Beyond technical performance, MOM Z14 sheds light on a crucial epoch of cosmic evolution. Through these observations, scientists are attempting to trace the earliest stages of star formation. A high concentration of gas at this time would have accelerated the emergence of massive stars, responsible for creating the first heavy elements. Their rapid evolution, explosion, and influence on their environment may have shaped subsequent galaxies. Each new galaxy detected so early in history challenges existing models. Thus, MOM Z14 becomes an open door to the most distant past, bringing us closer to the origin of the first galactic structures and the mysteries they hold. On the 27th of May, the James Webb Space Telescope focused its instruments on the galaxy cluster Abel S-Tone 63, revealing a cosmic landscape of unparalleled richness. This massive cluster, gathering hundreds of galaxies, exerts such a gravitational force that it acts as a natural lens, bending the light coming from the background. This phenomenon, called gravitational lensing, allows astronomers to dive deeper into the universe, revealing galaxies too distant to be perceived otherwise. By diverting their light, the cluster acts as a giant magnifying glass, unveiling shapes and details previously invisible. At the heart of this feat lies Hierarchical, Webb's infrared camera. It captures a shifted light, because as they move away, objects see their light stretch to longer wavelengths. This shift, an indicator of distance, pushes signals into the infrared. Thanks to Hierarchical's sensitivity, scientists can observe galaxies at the edge of time, made visible by the gravitational lensing effect. During this observation, Webb revealed a profusion of distant galaxies. Some appear barely perceptible, but are now accessible. Researchers speak of a deep gaze, for the combination of natural lensing and modern technology allows discovering previously unexplored corners of space-time. New structures emerge, spirals, subtle hues, galactic mergers, captured at the very moment of their encounter. With its mass, Abel S1063 acts as a revealer. By twisting light, it also unveils the distribution of invisible matter, dark matter. Though undetectable directly, it betrays its presence through gravitational effects. By studying the distorted images, astronomers map this essential component and learn more about its role in the construction of the universe. It's like observing a world through a distorting window. What would obscure our view becomes here a tool for analysis. The stretched or duplicated images tell a story, that of the cluster and its total mass. Scientists deduce the matter's distribution and confront it with their models to understand how cosmic structures emerge and shape. The observation of such faint galaxies also allows studying their chemical content and evolution. By analyzing their infrared light, astronomers detect elements like carbon or oxygen, witnesses to these galaxies' internal life. The more distant they are, the younger they appear to us. Thus, we witness the genesis of galactic forms long before the appearance of our own galaxy. The first images revealed have stunned the community. A swarm of luminous dots, some billions of light years away, has emerged. But beyond the visual shock, these images allow precise measurements. Luminosity, arrangements, clusters. So many parameters to refine models of cosmic evolution. Webb offers an unprecedented view of the universe's infancy. What Webb brings that is new is its ability to see what Hubble could not grasp. It cuts through the dust and perceives the light escaped from previous instruments. Invisible galaxies suddenly become identifiable, revealing structures we were unaware of. Thanks to NIRCam, unsuspected worlds emerge. Each galaxy, even tiny, may hold clues to the first stars. By studying these glows, researchers hope to trace back to the very beginnings, where everything started. Abel S1063 becomes a step on this path, an anchor point to explore the distant history of matter. Thanks to this natural lens and Webb's eyes, we are crossing an unprecedented threshold in the exploration of the cosmos. June 5th marks a pivotal date in contemporary astronomical exploration. On this day, the James Webb Space Telescope unveils the first results of the Cosmos Webb program, aimed at providing the most extensive cosmic panorama ever obtained in infrared. In a single day, scientists announce a series of remarkable observations, recording approximately 800,000 galaxies in a section of the sky, covering just over half a square degree, 0.6 SQ-DD, or about 2.1 SQ-MI. An area that, though minuscule at first glance, is like peering at a celestial confetti filled with distant galaxies, each with its distinctive characteristics. To understand the extent of this study, one must consider what a field of 0.6 square degrees, about 2.1 SQ-MI, represents. This term refers to the part of the sky explored by the telescope. Even if this figure seems modest, we must imagine that our eyes perceive only a tiny fraction of the cosmos. Consequently, such a surface already represents a vast field, especially when probed by the power of James Webb. Unlike ground-based telescopes, it is located far beyond the Moon, in a stable area of space called the Lagrange point L2. There, it can gaze continuously, free from the constraints of Earth's rotation, clouds, or stray lights. The Cosmos Webb program continues the grand survey cosmos conducted by Hubble, Spitzer, and other observatories. The arrival of James Webb and its advanced instruments designed for infrared usher in a new era. This light, with a wavelength exceeding that of the visible spectrum, allows the revelation of ancient galaxies, often hidden within clouds of dust, or too distant to be otherwise detected. Thanks to this technology, the program has been able to combine about 10,000 long exposures, meticulously stacked, to achieve exceptional sensitivity. Each exposure functions like a prolonged snapshot, capturing photons from space. These particles of light have sometimes traveled billions of years to reach James Webb. By gathering these thousands of images, scientists are patiently building an immense tableau, much deeper than a simple photo. The longer the exposure, the more faint objects reveal themselves. This allows for the study of the distribution, brightness, and morphology of galaxies, inferring how the universe has organized itself over time. Managing to catalog up to 800,000 galaxies in a single image is a feat. A few decades ago, detecting just a few hundred galaxies in a similar area was already an achievement. Now, James Webb takes us much further, with an impressive level of detail. This is the whole point of Cosmos Webb, to offer a statistical overview of the deep universe. What is the distribution of galaxies? How long have certain structures existed? Where does matter accumulate more? This panorama opens new avenues for finding answers. Beyond pure science, Cosmos Webb aims to become a resource accessible to all researchers. The images will be made public for 10 years, providing a treasure trove of information to anyone who wishes to exploit them. This approach is based on a simple conviction: the exploration of the universe belongs to everyone. The sharing of data is a source of inspiration for future research and a driver of scientific innovation. By combining these observations with other campaigns, past or future, researchers can refine their understanding of galaxies, their evolution, the role of the intergalactic medium and dark matter in the structuring of the cosmos. Many uncertainties remain about how galaxies cluster, form clusters, and then superclusters, drawing a vast cosmic web. Cosmos Webb, with its vast sample and precision, will allow progress in solving these mysteries. As always in astronomy, processing these data takes time. Teams compare, cross-reference, validate light signals, and attempt to untangle overlapping objects. Some of the 800,000 galaxies appear as mere smudges that only James Webb's expert eye could detect. Yet, even the most discrete ones can upend a model or reveal an unknown part of cosmic history. To produce this panorama, James Webb uses several instruments, including an infrared camera sensitive to light invisible to us. This type of observation penetrates interstellar dust and captures the light of very old or very young objects. Galaxies that formed a few 100 million years after the Big Bang emitted light stretched by time. By capturing this signal, James Webb reveals a time when the first stars were igniting, forging the elements that gave rise to life. It's June 12th, at the heart of a fascinating discovery made possible by the James Webb Space Telescope. Today, we're heading to a nebula named Cosmic Tornado, a spiral celestial object that has intrigued astronomers for months. Thanks to infrared observations, researchers have just published an unprecedented map of the magnetic field traversing this structure. The results come from a technique called polarimetry, which measures the orientation and intensity of the light's polarization. But what does this phenomenon mean, and why is it so important? Let's take a moment to understand it together. The nebula gets its nickname due to its elongated shape, a column of gas and dust standing in space like a funnel. This structure, stretching several light years or miles long, is shaped by powerful winds and jets emitted by young stars in formation. To explain its spiral appearance, it's important to understand that interstellar gas is very mobile, influenced by gravitational forces and pressures due to radiation. When these effects combine, they can produce spectacular flows reminiscent of a tornado. What is novel here is the use of infrared polarimetry, which measures the direction in which the light vibrates. One can imagine light as a wave oscillating in various directions. When it passes through dust grains aligned by a magnetic field, it takes on a particular orientation. By observing this orientation, astronomers can map the magnetic field lines, similar to tracing the lines of a magnet. To achieve this data, James Webb had to maintain exceptional infrared sensitivity. The study requires capturing very subtle brightness variations, sometimes less than 1%. Its detectors can isolate the signal from interstellar dust, even when it emits almost imperceptible light. Its instruments operate at extremely low temperatures, close to absolute zero. Around 260 degrees or 436 degrees, this limits noise and allows for reliable measurements. Once the data was collected, researchers studied the alignment of dust grains within the nebula. These tiny grains, smaller than a human hair, are oriented in space. This is no coincidence. They respond to the local magnetic field. In the presence of this field, they align like the needles of a compass. This behavior is valuable for drawing the map of the magnetic field. The measured strength reaches 200 microgauss. To give an idea, at the Earth's surface, our magnetic field is about half a Gauss. Here, we speak of microgauss because interstellar fields are much weaker. Yet, in this nebula, 200 microgauss represents a consistent value, considering the winds and internal movements. Knowing the strength of the magnetic field helps to understand the internal dynamics of the nebula, particularly how matter gathers or disperses. A strong enough field can slow flows, compress dust, and promote star birth. If it is too weak, the matter diffuses, hindering star formation. Another essential point is how infrared polarization allows probing different layers of the nebula. The deepest dust grains emit polarized infrared light, revealing the orientation of the magnetic field in depth. The larger the wavelength, the further the observation penetrates into the structure. James Webb is precisely equipped to cover this broad spectrum, which makes it unique. The interest of this discovery goes beyond the framework of this single nebula. The cosmic tornado becomes a true natural laboratory to study the early stages of star formation under extreme conditions. The winds and jets that compose it indicate intense activity, while the magnetic field structures the flows of matter. Together, these elements provide a valuable view of the mechanisms at work in the beginnings of a stellar system. The unparalleled precision of the James Webb in detecting polarization paves the way for new studies. Following this initial success, scientists plan to apply the method to other dusty areas in our galaxy or in more distant systems. The goal is to create a database on the magnetic fields of the universe to understand their origin and evolution. This could shed light on the history of matter from the earliest times until today. Thanks to these data, researchers can test more advanced models simulating the effect of magnetic fields on structures like this one. They are also trying to determine if these fields can last millions of years, durably influencing the shape and evolution of the nebula. Upcoming studies, already underway, will again use infrared polarimetry to reveal more secrets about the birth of stars. A step closer to understanding the cosmos. June 17th marks a turning point in the exploration of the universe when the James Webb Space Telescope directs its instruments towards a singular galaxy nicknamed Jellyfish and referenced under the name Cosmos 2020-63-5829 that we have already seen earlier. Located at an immense distance, over 100 million light-years or about 621 million miles, this galaxy astonishes astronomers with its silhouette resembling a floating creature with luminous filaments evoking tentacles. These long trails are composed of stars and intense zones of star formation. This structure, revealed through a recently deployed infrared technique, opens a new field of study on the physical processes shaping these particular galaxies. The Jellyfish galaxy is distinguished by a phenomenon called ram pressure stripping. When it rapidly moves through an environment filled with diffuse gas, this medium exerts enough pressure to strip away its outer layers. It's as if an object rushes through a thick fog, losing fragments along its path. In this case, it forms a trail of ejected gas in which new stars are born. At the heart of this tale, scientists observe bright regions of ionized hydrogen. These zones, called H2, are dominated by hydrogen whose electrons have been stripped by the energy emitted by young massive stars. These zones, very bright in infrared, indicate intense stellar activity. This means that even in the expelled matter, new stars continue to emerge, stimulated by the gravitational effects of the ongoing disturbance. The Jellyfish galaxy thus becomes a unique laboratory to observe the birth of stars under extreme conditions. This phenomenon is linked to what astronomers call quenching, which means the gradual cessation of star formation. At first glance, such upheaval could signify the end of all activity. Yet, the data reveals that the activity shifts towards the edges, along the tail. New regions of formation appear, prolonging the galaxy's vitality before the definitive halt sets in. Researchers aim to identify the moment when this transition becomes irreversible. To understand this evolution, the galaxy must be placed in its environment. Galaxy clusters are dense areas filled with gas. By traversing them, a galaxy can experience pressure strong enough to lose its gas. Visually, a compact central region can be distinguished, surrounded by filaments extending behind. These filaments, made of dust and gas, sometimes transform into sites of matter condensation, where new stars are born. Researchers focus on the luminous contrasts between the center of the galaxy and its filaments. These distant zones shine thanks to young stars in full bloom. This raises a question: how can a galaxy that loses its gas still produce it? One possible explanation is that the compression of moving gas causes, in some cases, its condensation, favoring the emergence of bright clusters. This unexpected interaction reveals the complexity of the processes at play. The observation of these luminous filaments has been made possible thanks to the infrared capability of James Webb. Unlike optical instruments, Webb captures the heat emitted by dust clouds and reveals details invisible to the human eye. Its sensors have allowed us to distinctly see the elongated structures and the regions rich in ionized hydrogen. It becomes clear that this galaxy is not simply disintegrating, but continues to produce new forms of stellar life. This system also provides a unique opportunity to study the end of star formation in extreme environments. By analyzing the distribution of young stars and their chemical composition, researchers trace the galaxy's history, its trajectory, the amount of gas lost, and when all activity will cease. These data are inscribed in the heavy elements, in the variations of temperature and density, drawing an accurate portrait of this evolution. We are on June 19th, the day a major announcement was made thanks to the observations of the James Webb Space Telescope. For the first time, researchers have established detailed statistics on protoclusters, these gestating structures that will one day become galactic clusters. 1,678 protoclusters have been counted, a figure that renews our understanding of large-scale formation in the universe. The James Webb Telescope, placed at the Lagrange point L2 and equipped with a 6-meter 60, 22 feet, segmented mirror, has transformed our way of studying these distant zones. Its ability to observe the infrared allows it to penetrate cosmic dust and capture the light emitted by growing galaxies. For the first time, the structure of these future megastructures becomes readable with unprecedented precision. A protocluster is a grouping of evolving galaxies, some of which are not yet fully formed. Collisions, mergers, and interactions are frequent, triggering intense bursts of star formation. Over time, these edifices transform into massive assemblies comparable to today's large galactic clusters. Protoclusters directly testify to the way matter assembles on a large scale. Before James Webb, identifying these structures was difficult. Previous telescopes, less sensitive to the infrared, struggled to discern these groupings veiled by dust. Only partial estimates existed, based on the fragmentary detection of embryonic clusters. Today, with the power of the 6-meter 60, 22 feet, mirror and high-resolution instruments, the counting of more than 1,670 of these large assemblies is confirmed. According to the publication relayed on phys.org, this massive count opens a unique window into the past. Each spotted protocluster provides clues about the abundance of gas, the presence of satellite galaxies, and the ongoing gravitational dynamics. The goal is to measure the growth rate of these structures and understand how they become stable several billion years later. To conduct the investigation, astronomers have combined observations from the infrared camera and the spectrograph on board the telescope. The former reveals the spatial distribution of galaxies, while the latter studies the light spectrum to extract chemical composition and internal movements. Data are then analyzed by advanced algorithms compared to numerical models. This census also provides valuable indications about the environment in which these protoclusters are born. Researchers want to know if the local density accelerates the birth of stars or enhances interactions between nearby galaxies. Some believe that a very compact protocluster will see rapid mergers occur, while a more extended ensemble will keep its galaxies intact for longer. Understanding this dynamic is essential to tracing galactic evolution. The results also show that dark matter plays a central role in the organization of protoclusters. This invisible component, perceived only by its gravitational effects, seems indispensable to explain the scope and coherence of these structures so early in cosmic history. Each protocluster becomes a test for current models, which must integrate its presence in their calculations. June 19th marks the official culmination of this census, validated by the scientific community after months of analysis. For researchers, it is the starting point of a new chapter, studying each protocluster in detail, searching for possible anomalies, detecting active black holes, or singular galaxies undergoing transformation. Beyond the simple map, the objective is to finally analyze the chemical composition of these groups. The detection of heavy elements like carbon, oxygen, or iron indicates the level of stellar maturity reached. Each proportion of the element traces a history of explosions and fusions of massive stars. Knowing this stage of evolution sheds light on our understanding of cosmic development. Researchers also want to refine the timeline of protocluster formation. Some models suggest that a large part of them already existed less than 2 billion years after the Big Bang. Other theories consider a slower growth, influenced by the distribution of dark matter. By collecting more data, James Webb will help settle these scenarios and enrich our vision of the past. This investigation also offers a point of comparison with the more recent clusters we observe around us. By confronting these two generations, scientists identify the mechanisms that remain constant and those that change. This includes galactic interactions, mergers, or gas losses due to the internal currents of the clusters. The study of June 19th is thus the first milestone of a much broader exploration. Teams will continue their work by filtering infrared data to uncover other, more distant or more discrete protoclusters. They are also looking to improve distance measurements, as knowing the exact distance is crucial for placing each event in the universe's chronology. This assessment goes beyond mere statistics. It reveals the diversity of conditions that lead to the formation of large clusters. Taking into account stars, gas, dark matter, and collisions, astronomers paint a complex portrait. These results are already prompting a re-evaluation of certain parameters, a promise of the future. On June 25th of this year, astronomers worldwide hailed a major breakthrough in the search for planets located beyond our solar system. Thanks to the James Webb Space Telescope, a particularly intriguing exoplanet named TWA-7b has been distinctly identified. Located about 110 light-years, or about 660 trillion miles away, this planet becomes the first to be detected by direct imaging with this next-generation observatory. This technique allows capturing the light emitted by the planet itself without resorting to indirect methods like transits or gravitational effects on its host star. Named after its star TWA-7 from a young stellar group studied for a long time, this planet has a mass comparable to that of Saturn. Generally, detecting an object smaller than Jupiter by direct imaging is challenging because it emits less radiation. The James Webb Telescope, with its mirror over 6 meters or about 20 feet and its sensitive infrared instruments, captured the glow of TWA-7b through the shine of its star, revealing its presence clearly. Direct imaging consists of pointing an instrument at a star and blocking its light with a specialized device. By occulting this light, the faint radiation emitted by the planet can be distinguished. For TWA-7b, researchers used the telescope's MIRI instrument, which observes in the mid-infrared. This band clearly reveals cool or moderately warm objects. Thus, astronomers were able to spot the planet, estimate its temperature, and its trajectory. A remarkable outcome. The TWA7 system is part of a very young stellar association whose age does not exceed a few million years. This youth often favors the presence of gas and dust disks where planets are born. Scientists believe that TWA7b is still in a cooling phase, which explains its measurable heat emission. Its temperature would exceed several hundred degrees Fahrenheit, even though more precise measurements are still underway. Complementary observations are being prepared to better understand its atmosphere and evolution. So far, most planets detected by direct imaging have been more massive than Jupiter. Spotting a planet the size of Saturn is therefore an important advancement in the detection of smaller worlds that are just as interesting. To estimate the mass of TWA7b, researchers analyze its infrared brightness and compare it to theoretical models of planetary cooling. They deduce that this planet is Saturnian type, enriching the catalog of known exoplanets. A beautiful demonstration of the precision of the James Webb Telescope. The distance separating TWA7 from Earth, 110 light-years, approximately 621 trillion miles, remains modest on the scale of the galaxy. 1 light-year equals nearly 10 trillion kilometers or 6 trillion miles. Astronomers use techniques like parallax to accurately assess these distances. Astrometric catalogs have made it possible to set that of TWA7, confirming that this system is nearby. At this distance, the telescope can collect enough light to establish a detailed profile of the planet. This discovery sheds light on new aspects of the formation of gas giants in their youth. By studying a planet of Saturnian mass, scientists gain access to little understood mechanisms, such as the accretion of gas into the atmosphere. By directly observing the infrared emissions of TWA7b, they access its thermal structure and the composition of its gaseous envelope. This allows this planet to be compared with what Saturn might have been like in its early days. These advances open avenues for understanding planetary systems. Beyond this detection, researchers will now analyze the infrared spectrum of TWA7b to detect molecular signatures. They hope to see the appearance of water vapor, methane, or ammonia, signs of active chemistry in its atmosphere. Even though this planet is not habitable, studying its components will provide valuable information about the chemical reactions taking place in planetary disks and will guide research toward worlds more conducive to life. We move forward in time a few days and dive back into space. On July 8, 2025, a group of astronomers is observing an already famous area, the galaxy cluster Abel 2744, used as a natural magnifying glass by gravity. Beyond this cluster, they spot an embryonic cluster of galaxies called a protocluster, whose light has taken more than 13 billion years to reach us. In astronomers' language, the light is so stretched that its redshift approaches 8, meaning we are observing the universe when it was not yet 2 billion years old. There, unexpectedly, the heart of this group appears already mature. Well-formed galaxies, containing many stars, and above all, an organization resembling that of the great clusters of our time. When scientists talk about redshift, they describe a phenomenon that's easy to understand if imagined like an ambulance siren. When the ambulance moves away, the sound is less high-pitched. For distant galaxies' light, it's a bit the same. As the universe expands, it stretches this light, making it redder. The further the object, the more its light is shifted. This proto-cluster is therefore very far in time and space. James Webb, with its near-infrared camera, called near-infrared camera or NIRCam, is designed to precisely capture this stretched red light. Observing it, researchers detect chemical signatures and light patterns that indicate the presence of stars already relatively old for a time so early after the Big Bang. Protocluster is like a city district under construction that already has a very active downtown. Usually, one would expect to find bricks everywhere, temporary structures and construction sites, not well-decorated buildings. Here, however, the downtown of this protocluster is already present. Massive galaxies grouped at the core, stars forming, gravitational interactions providing a solid framework for the whole. This rapid maturity challenges our models. Astronomers wondered whether large structures took billions of years to slowly consolidate. This observation suggests that at least some of them organized more quickly, possibly because the matter was concentrated in particular areas, or because gravity was amplified by a denser distribution of dark matter. How does Webb see this? It doesn't just take beautiful images. In addition to Hierarchical, instruments analyze the light to break it down into a very detailed infrared rainbow, much like separating each color to know what an object is made of. This process is called spectroscopy. Thanks to it, we can guess the composition of the gas, estimate the mass of stars, their approximate age, or even detect the movement of gas and stars in these young galaxies. Astronomers have used deep imaging and spectra with fine enough resolution to distinguish details we could not see before. They then compare these observations to numerical models to determine if the observed structure truly corresponds to a growing protocluster, confirmed by the density of galaxies and chemical richness of the core. Behind this achievement lies a teamwork between nature and technology. The cluster Abel 2744 acts as a gravitational lens. Its enormous mass warps space and bends the light from even more distant galaxies. It's like looking at an object through a curved glass. It magnifies or distorts the image. Thanks to this cosmic magnifying glass, Webb receives more light from these distant galaxies than it would without this help. The protocluster, named A2744Z79OD, whose name is difficult to pronounce, was thus scrutinized in detail. Astronomers have confirmed that what they were seeing wasn't a mere fortuitous alignment, but a physical grouping of galaxies evolving together. For the public, we can simplify. Imagine the first season of a cosmic city. We thought that initially, everything was still under construction with streets traced hastily in shacks. However, we discover that some avenues are already paved, buildings are standing, and life is active there. This implies that the available energy, the amount of gas, gravity, and the environment in which these galaxies formed have accelerated the process. Researchers will delve further by analyzing the chemical composition of these galaxies. The presence of oxygen, carbon, and other heavy elements shows that at least one generation of stars has already lived and exploded, enriching the gas. Cosmic time seems denser than previously believed. Barely 2 days later, on July 10th, 2025, the telescope celebrates its third scientific anniversary. To celebrate this anniversary, NASA releases a new image, like a birthday gift, of the Cat's Paw Nebula, also called NGC 6334. This nebula is a region where young massive stars are born and grow. The name Cat's Paw comes from its shape, reminiscent of a feline's pad with rounded and marked areas like prints. Webb's near-infrared camera, NIRCam, sees details never seen before: filaments of dust, bubbles sculpted by the pressure and light of stars, and bright areas where the gas is illuminated by intense radiation. What we see in the image are giant clouds of gas and dust made luminous by the ultraviolet and infrared light of forming stars. When a star is born, it emits energetic radiation that pushes the surrounding gas. This gas moves, sculpts, and hollows into cavities. We can distinguish grains, bubbles, and arcs. These shapes result from a violent dialogue between gravity, which attracts the gas toward the nascent stars, and stellar winds, powerful flows of particles that these stars eject. These winds, combined with the pressure of light, push the matter outward. The result draws complex structures, which Webb reveals because it sees in the infrared, a wavelength that our eyes do not perceive but penetrates dust more effectively. In this nebula, the temperature of the gas varies tremendously. Some areas close to the stars can reach several thousand degrees Celsius, or several thousand Fahrenheit, while more buried pockets, protected from direct light, remain much colder, sometimes just above -200 degrees Celsius, or -328 Fahrenheit. The telescope does not directly measure temperature as a thermometer would, but the infrared light provides clues. The hotter an object is, the more it emits a certain amount of infrared light. By comparing these emissions, one can estimate the temperatures. These heat nuances help astronomers determine where the gas is compressed, where it collapses, where new stars might form in turn. This anniversary snapshot also has an educational function. It shows the general public how stars are born and how they transform their environment. Massive stars, larger than the sun, live fast and die in supernovas. During their lifetime, they are veritable factories of heavy elements, forging carbon, oxygen, and other atoms essential to life as we know it. By sculpting the nebula around them, they disperse these elements into space. When they explode, they further enrich the interstellar medium. Images from Webb are therefore portraits of this ongoing story. They allow us to follow the effects of a star in its neighborhood, just as one would observe the ripples after a stone falls into a lake. The cat's paw. Nebula is not just beautiful. It is a natural laboratory. In its clouds, dust plays a central role. Dust grains are tiny, much smaller than a grain of sand. They absorb and re-emit light. They also serve as surfaces where molecules can form. These are sometimes the first steps of more complex chemistry. By observing these grains and how they are heated or cooled, we can learn more about the chemistry of interstellar environments. Webb allows mapping the dust in infrared, which provides information about its density, composition, and role in star formation. The bluish color that illuminates certain areas in the official image does not really mean that the nebula is blue to the naked eye. The colors are often chosen to represent specific wavelengths of infrared light. In other words, the hues are translated to make visible what our eyes cannot see. Each color corresponds to a filter that highlights a certain emission of gas or dust. NASA and its partners select these colors to tell a story, where the hottest stars are, where the dust is, where the gas is compressed. It is a visual language designed to popularize scientific data while maintaining their accuracy. Thus, in just a few days, James Webb has taken us from an already advanced cosmic city to a bustling stellar nursery. This ability to travel through time and space, from the extreme distant past to our galaxy, is one of the great strengths of the telescope. But the surprise does not stop there. In mid-July, an announcement thrilled the community of astronomers. 14 galaxies that could be called Sleeping Beauty were detected in the early period of the cosmos, less than 1 billion years after the Big Bang. These galaxies have not produced stars for 10 to 25 million years. On a human scale, that's very long, but on a cosmic scale, especially so early, it's a blink of an eye. The nickname Sleeping Beauty comes from the idea that they have fallen asleep. They have stopped forming stars, while their cousins of the same era are in a full frenzy of star births. How can a galaxy stop so early when the universe is teeming with gas? Researchers suggest an explanation. A sudden burst of stars may have consumed or expelled the available gas. The winds from these massive stars and the explosions of supernovas may have ejected or heated the gas, making it unable to condense again to form other stars. As a result, the galaxy finds itself without cold fuel, like an engine stalling on the road. Usually, it was thought that galaxies in this young universe followed a continuous pace of star formation. However, this result suggests a burst behavior, periods of intense activity, then pauses. 10 to 25 million years of pause is nothing on the cosmic scale, but it is enough for us to talk about a dormant galaxy. This shows that galactic evolution is more chaotic, more varied than previously imagined. The masses of these galaxies are also surprising. Some are light, with the equivalent of 40 million times the mass of the Sun in stars, while others are already very heavy, up to 30 billion times the mass of the Sun. This range of masses makes the phenomenon even more intriguing. How did Webb spot these sleeping beauties? Once again, thanks to spectroscopy and infrared light. A galaxy that forms stars will shine differently than a galaxy that is merely conserving its already born stars. The chemical signatures in the light indicate whether new hot stars are forming. In the case of these galaxies, fewer typical signatures of gas ionized by young massive stars are found. On the contrary, we detect indicators of an older star population and an emission deficit that betrays the absence of recent formation. The spectra thus paint a portrait: little renewed gas, few ultraviolet sources, and relative silence in regions where one would expect stellar nurseries. This discovery is not only spectacular, it pushes researchers to launch a special program, dubbed Sleeping Beauties, to examine these galaxies more closely. The goal is to precisely quantify how long they sleep, what triggers the halt, and what rekindles star formation afterward. Computer models will have to incorporate these pauses. Until now, many assumed a continuous flow of stellar formation in the early universe. Now, mechanisms of stopping and restarting must be anticipated, perhaps linked to how the energy from massive stars propagates in the interstellar gas, or with the presence of central black holes that might expel gas through jets. Understanding the idea of feedback can help. Imagine a campfire. You feed the fire with wood, the gas. If the fire becomes too intense, it can char the remaining wood. Surprisingly, this can make the wood too dry or too distant to be consumed correctly. In a galaxy, massive stars are somewhat like that too intense fire. They cast violent winds and, by exploding, heat or expel the gas that would otherwise have served to nourish the birth of new stars. The galaxy finds itself lacking cold fuel. It must wait for the gas to fall back, to cool down, or to come from outside. This pause becomes an obligatory passage and explains the temporary silence. To verify the duration of these pauses, astronomers will compare these galaxies to other more recent objects in time. We have indeed seen red and dead galaxies in the more recent universe, but they were much older. Finding such cases so early changes the game. Astronomers will also use other observatories, sometimes ground-based, to complement Webb's data, for example in radio to see the cold gas or with millimeter telescopes to detect dust and molecular gas. By multiplying approaches, we'll know if these galaxies wake up quickly or if they extinguish definitively before joining larger clusters. What we retain from these three close events, the very evolved Protocluster, the Cat's Paw Nebula sculpted by stars, and the sleeping galaxies, is the diversity of paths in the universe. On one hand, enormous structures that build faster than expected. On the other, stellar nurseries that bubble with activity. And in between, galaxies that doze off after a growth spurt. The universe is not a linear and uniform story. It is a mosaic of rhythms, a symphony of cycles, of births, stops, and starts. Webb, by observing in infrared, allows us to read the pages that dust masked until now. If we return to the Protocluster, the researchers will now attempt to estimate the amount of dark matter that keeps this core compact. Dark matter is invisible. It does not emit light, but exerts gravity. To map it, one observes how it deforms the background light or the rotation speed of galaxies. Defining its distribution in a protocluster, this young will help determine whether dark matter quickly structured itself, providing a solid framework around which galaxies lit up. These are crucial clues for testing our cosmological theories. In the Cat's Paw Nebula, the story is different. Astronomers will follow the evolution of the cavities carved out by stellar winds. When gas is pushed away, it often ends up gathering elsewhere, like dust being swept into a small pile. In space, these piles can become new sites for star formation. This results in a cascading sequence, today's massive stars sculpting the gas that will create tomorrow's stars. Webb's infrared images will be compared to photos taken in other wavelengths to detect future stellar cores, still cold and invisible in visible light. Concerning the sleeping galaxies, an important point is the quality of the data. The study describing them has not yet been validated by the entire scientific community through the peer review process. This means the results could change, be adjusted, or even contradicted if other teams find biases in the analysis. But even so, the idea that pauses already occurred this early is very stimulating. It encourages other groups to look for similar clues in major cosmic surveys, to cross-reference Webb's data with those from other programs. The goal is to obtain a solid statistical view, how many galaxies sleep, for how long, and at what specific moments in their history. More surprises are surely on the way, carried by the light of galaxies and nebulae still hidden in the infrared depths.